to that, okay? If you go saturated, it'd be like butter, regular butter that you were using, stuff like that.
Okay.
But that's a little much. So people have chosen that, because you see, margarine, you know the margarines? When they made margarines at first, everybody got wild about it, said, we love this, margarines. What were margarines? They took corn oil or some other oil, and they treated it so it became hardened, okay? And it was called hydrogenation, which means putting the hydrogens in there. You got a saturated fat, and it lost some of its beautiful qualities, and people didn't know that. So they went gung-ho on the margarines. And there was another really bad part of that, which is the trans fats. The process actually put trans fats in there, and that's the stuff that you don't want. So they had gone out for the margarines, and it really ended up being a big disappointment. Okay. You can go in the store and even look to see if there are any trans fatty acids, and it'll say no trans fatty acids in this product. So they're careful about that. Not always, but there are some people that are really watching that, because the trans fatty acids are actually worse for you than the plain old, we believe, than the plain old cream and butter, which is ironic, isn't it? You run away from the one, you find out actually it's better than the other one you thought was good for you. All right, well, that's just part of life.
Just to, so the fatty acid that has the kink is
Yeah.
gonna represent a saturated.
No, the other one.
Okay.
Saturated means no kinks.
Saturated.
Unsaturated means kinks. There you go. This is page 48. This is interesting. There we go. This is interesting. So, notice there's a carbon here in the center. There's a hydrogen here. Over on this side, you've got a nitrogen and 2 hydrogens, and they call that an amine group. Over here, we've got a carbon with a double bond to oxygen, plus a single bond to an oxygen with a hydrogen. That's the acid group. Those are organic acids that have that. This is not hydrochloric acid, sulfuric acid, no. This is organic acids. And you got this on this side, this on this side, acid group, amine group, and what's it sound like? Amino acids. What about the R? In algebra, if you have an unknown, what do you call it? X, Y, stuff like that. You can call it T, you can call it whatever you want, omega or something else. But here we have an R as a placeholder, actually a variable in here. So tell me what you think the simplest thing could be for an R here.
Carbon.
That isn't quite as simple. That's not quite as simple. Hydrogen. Hydrogen is the really simple one. So all you have is just a hydrogen here, but you have an amino acid. Which one? You have the simplest amino acid, because they all have this kind of form, except the only difference between the amino acids is what their R is. It's the only difference. You can be fancy, but it could be as simple as just a hydrogen. Then we have a name for this. The simplest amino acid is glycine. 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 You should be able to write that formula, shouldn't you? You should. Because what would you have? A central carbon with a hydrogen, and then you put the N and the 2 H's over here, and you put the carbon with the double bond to oxygen plus single bond to oxygen plus a hydrogen. And you got it. That every amino acid has this part. It's just the only difference is what is the R. Any questions?
So, what do you mean exactly by like what is the R? Like it can change?
The R is like whatever you want to make it. Yeah, it's a variable. So what could we put in here? Well, just a plain old hydrogen would work. And that's the simplest thing you could choose. Could you put a carbon and 3 hydrogens there? Yes. Can you put fancier things in that? Oh yeah. You could even put rings in here. But there's a limited number, because how many amino acids are we aware of? How many amino acids are we aware of? About 20. Yep, about 20. Okay. So this was the simplest one. What was its name?
How was it glycine?
Glycine, it was, good. All right. So what would you do with amino acids?
Build protein.
Build proteins, okay. So, how many proteins, how many amino acids to make a protein? 51 or more? 51 you have to, because if it's 50, it's still not a protein. Okay? Are proteins useful? Are they around? Oh yeah, they are. Have you seen any beauty aids or soaps or things that say they have collagen in them? Well, here's collagen, and that happens to be a protein. It's found in all connective tissue. It's the oh, look at that. Did you see that? The single most abundant protein in the body. Boy, does that ever have an odor, don't you think? I think so. Single most abundant protein in your body. It's good to know.
Collagen?
Collagen. Yeah. What would you use it for? Tensile strength. Like in bones, there's collagen? Yeah. In tendons? Yeah. What do tendons do?
Joint muscles.
Muscle to
Bone.
Bone. Okay, what about ligaments? What do they do? Bone to bone. Sorry. So they even have some collagen in them. Okay. And I think, maybe I shouldn't say this, but I think that like you can go to the store and get broth that's made from chicken bones or stuff like that. I think you're getting collagen in that. Here's a red one. Look at this. What's red in your blood?
Erythrocytes?
Yep, because of, it's actually because of, not collagen in this case, it's the hemoglobin. That's the red stuff in your blood. Is it good? What's it do?
Transport oxygen.
It carries oxygen. One hemoglobin molecule can carry how many oxygen? 4 of them. Look at that. Could it carry less? Yeah, it could. This is a really good molecule. The hemoglobin molecule transporting oxygen. Okay. We've done some of that in AP2 already. Well, look at this. The nubbies. What do the nubbies do? Touch? What are they touching here? They go for the fin and then filaments and form a
Cross bridge.
cross bridge on the pit hole. And then they're going to let go of something, 2 things. What was it? ADP and the phosphate. And now what can they do?
Do the power stroke.
Power stroke, exactly. And when they do the power stroke, they move the finactin filament. Where's it go? The ends start to try to get together. So you're bringing the finactin filaments closer together, and that's drawing the what closer together?
The C disc.
C disc, and that shortens your sarcomere, and that's contraction. So we learned about that. We didn't know about it, but we learned about it. So that's good. Well, did you realize those are proteins? The nubbies, myosin. Myosin molecules are actually proteins, and the finactin filaments, the olives are proteins. So you're starting to see, proteins are a big deal. Yep, they are. Collagen was a protein, and you have chemical messengers in the blood that are proteins a lot of times. Who are they? They got secreted there. Who are they? Hormones. Yes. Okay, how about this? You're gonna love this one. This is pretty wise, isn't it? What would be a wise thing to do? Stick a whole bunch of Ys on a virus, and you know what the virus does? Nothing. It can't. You just messed it up. You put Ys all over the place. You know what the Ys are? Antibodies. So that sounds like a trick of an antibody, isn't it? Coat it with antibodies, and the virus is powerless. Okay, you've neutralized the virus. So they would say that's neutralization. Who does neutralization?
The immune system?
Antibodies shaped like lines. Okay. So we've been in this already in AP2. We've done the chapter, the immune chapter. In fact, that's what they just had a test on. Okay, their test too. They just had that. All right. So are you getting an appreciation for proteins? Yes.
So hormones are a protein, but they
A
require.
lot of them are, not all, but I think a lot of them are.
But they're made from cholesterol and fatty acids.
Yeah, that's a good question. Let me put it this way, some hormones are proteins. The cholesterol is not a protein, it's a fat, it's actually steroid fat. Yeah. So I wouldn't go too far in that at this point.
Okay.
But, yeah. Actually, I was thinking enzymes are mostly proteins. And I wanted to say they all were, and make it simple. I said, they're all proteins, but I got corrected. Somebody said, no, they aren't all that way, but most of them are. That was my final settlement. So I like thinking of them as proteins, but I had to not do that because there are some of them. Okay. All right, now we're looking at the next page. We're going to look at page 50. Look what they did with your amino acids. They stuck it into a chain. They made a protein. Again, how many did you have to have minimum?
51.
51. Could you have 100?
Yes.
Yep, 51 or more. Amino acids makes a protein. And if you were a little kid and you had a long string of these things, pretty soon, and you're sitting on the floor, what would they be doing with it? Think about being a little kid and you had this long string of stuff. What would you do? You can think about your dog. What would your dog do to it? Chewing it. Little kid's gonna be doing this, right? Well, if you did that, you'd have what's called a helix. This bended thing, helix. Okay? A single helix there. Or you could take it and go back and forth and make a pleated sheet. So these are two secondary structures you could make with the primary structure being amino acid to amino acid to amino acid to amino acid. See, what else could I do? Oh, you could bunch these together, bundle them up, and make a blob. Okay, a blob. That would be a tertiary structure. Tertiary. Secondary, tertiary. What if you put two blobs together? You can make a quaternary structure. So in our body, our proteins can be in these different forms. Okay. Now let's go on. All right, I'm going to check out your imagination. Are these black holes? No. What do they look most like to you? We're doing an ink blot test here.
Teeth?
What'd you think? Dog snout, what? Oh, snout, okay. Yeah, there is some of that. See anything else? It looks like teeth, doesn't it?
Yeah.
If you were in a nursing home and you found this on the floor, what would you suspect? Come on, what would you suspect? Dentures, that's right, that's what I think of when I see these. It's like pieces of denture here. All right, that's fine. It's not black holes, but it is fine. So the darker part is the enzyme with active sites. And what are you gonna put in the active sites? The teeth. And the teeth are representing substrates. So enzymes work on substrates, okay? Substrate or substrates. And they go in the active site. And they get close, pretty close. And guess what happens? They actually bond, okay? And they release water. So what kind of action was this? Dehydration synthesis, and off goes our new product, a dipeptide, because these were amino acids. Okay, that's interesting. I like to use the comparison. So you have quite a bit of money. You're not short on money, and you have lots of friends because you socialize. You are a gabber. You just talk to people and you have a good time. And you say, you know, we've got these people that are just so nice. If they could just meet each other, be the matchmaker, and you're going to try to get them to meet each other because you just know they're gonna like each other. So what do? You have a dinner party, and you put little labels on the plates. Who sits here, who sits there, and amazingly, they're sitting beside each other. Can you imagine? And nobody has figured this out yet. So you put them at these plates right beside each other, and while you're waiting for the rolls and the other stuff to come, what are they doing? What? Talking. And they find out they both have this kind of dog at home, the same dog, and they're excited about that. Yeah, do you take yours out for a walk? Well, of course I do. How often do you do it? Well, I do it 2 times. I like to do it 3 times a day. And they say, yeah, I like 3 times a day. Pretty soon they're talking about dog food. They're talking about all kinds of other stuff. Look what happens. All you had to do was get them close together, and wow, you made a match. Okay? That's pretty fun. That's pretty good. Okay? And they lived happily ever after. That we had to add too. Okay? Well, if they don't live happily ever after, what can they do? They can come back, sit in the seats, and get a divorce. Okay? That's how enzymes work. They can put things close enough that they bond together, or bring them back close enough that they split apart. Now, some enzymes can do both. Others can only do one. They can't do both of them.
So if they were going to split apart, they would use the same enzyme?
Yep. In this case, this same enzyme, what was it doing? All it was doing was getting them close enough. That's all it was doing. Okay? It wasn't giving them some extra caffeine drink or something. They were doing that. Okay? How long could you keep using this enzyme? Yeah, it's like, it's undetermined. You could keep using it and keep using it and keep using it. You don't have to make a new one each time. Okay? And you keep making this stuff. This is how your body's enzymes work. They can do some of this very same thing. And our metabolism reactions are based on enzymes. Okay? So that's kind of a neat one. It's kind of neat. And now, would you climb the stairs that look like that? What if it was a little creaky? No? I don't think so. Next, there's an elevator over here. Well, you gotta watch those too. There's stairs here. I'm gonna go up the stairs. Okay? This spiral ladder is actually what molecule? DNA. Full name? Oxyribonucleic acid. Is it one swirl? 2 swirls. That makes it a double helix. Double helix, not a single one. A double helix. Now, this double helix has steps on it. Again, would you test those steps before you went up there? Yeah, what if you stepped on one and it came apart? You would say, that's it, I'm going back down. Okay? So these steps on a ladder are called, what was it again? Yeah, you're jumping ahead on me, but that's true. Okay. People climbing ladders are stepping on the
Rome.
rungs. The rungs, I said that in class and nobody knew what it meant. They never heard that. So, you know, I say steps now because they probably can figure out what that is, okay? These steps are actually nitrogenous bases. Nitrogenous bases. So, these are nitrogenous base pairs. So what are the steps on this? Nitrogenous base pairs. What goes with T? A. What goes with G? C. Oh, you're just not very imaginative. What else? That's it. It's so simple. G's go with C's, T's go with A's, and so you can make your step that way. And they just colored them for the fun of it. Okay. So what are the steps? What are the rungs on a DNA ladder? Nitrogenous base pairs. What if you say nitrogenous bases? That's not enough. Don't expect full points on something like that. Nitrogenous base pairs, that means more. Okay. What about the rails? What are the rails? Which pentose sugar? Deoxyribose, because this is DNA. You wouldn't have any ribose here. And they're alternating with phosphates. So you're holding onto the rails as you're going up the spiral staircase. And the steps again are nitrogenous base pairs. Why do they call them nitrogenous? Because they have nitrogen in them. Yes.
Where can we find that in the book?
You want one of these spiral staircases?
No. I don't know how to spell it.
Which one?
Nitrogenous bases.
Nitrogenous. All right. Well, that was interesting. Here's your key down here. It says the yellow ones are thymine, the green ones are adenine, the blue ones are cytosine, and the reddish ones are guanine. Now we come up here at the top and we say, what do we see here? We see a nitrogenous base with a pentose sugar with a phosphate. Isn't that what this and this and this is? Yes. So you mean that's all this is a whole bunch of this nitrogenous base with a pentose sugar with a phosphate? Yes, and those are called nucleotides. So DNA is composed of nucleotides. What about RNA? It's also nucleotides. Now they can be different because you don't see any U's on here. But in RNA you have U's instead of T's. So what would the U go with? A, that's right. Okay? But you'd have to be talking RNA because DNA would not have any U's in there. Okay? So we find out this twisted ladder is composed of nucleotides joined together by weak bonds. That's what they're showing here. Weak hydrogen bonds. You can just say hydrogen bonds. So we join the nucleotides in the center with hydrogen bonds, weak hydrogen bonds, and that's why I said test out the ladder. If you're going to step on that, you don't want those weak bonds to break. But that's what they're famous for. Weak bonds are famous for being easy to break and to make. So, what could you do? Zip it and unzip it. I knew this code was going to be useful. Object lesson. So having hydrogen bonds, even though they're weak, could be actually advantageous. Why in the world do you want to unzip DNA? To replicate it, make more. And exactly. So it's really good to actually have hydrogen bonds here. All right. So we'll look at that in a little bit. Any questions so far? Okay, I'm going to show you. Yes. What?
So it's safe to say that a nucleotide is a phosphate group, has sugar and a nitrogenous
Yeah,
base.
pentose sugar
Pentose sugar.
and a nitrogenous base. If you've got a phosphate, a pentose sugar, and a nitrogenous base, that's a nucleotide. You could build DNA that way, you can build RNA that way,
It was a phosphate, pentose sugar,
and a nitrogenous base. Now, it depends which is which, you know, U goes with RNA, it doesn't go with DNA. And thymine goes with DNA and not RNA. So you have to watch that kind of stuff. And here's your old friend, look at this. Tell me, who's your old friend? I see an adenine and a ribose, what's that? Well, it's right here, I'm gonna show you it anyway. This is adenine plus ribose equals adenosine and 3 phosphates. ATP, that's what ATP is. Adenine, ribose plus 3 phosphates. What do you use it for? What? Energy. How do we get the energy out of this? Break off a phosphate. There you are, brutal strength. Break it off. And energy comes out. And in your cell, you can use that for doing processes. Okay, so that's okay. What would you have left? A DP and a phosphate. And who's going to fix it back the way it used to be? Regenerate the ATP. Mitochondria. If it's singular, mitochondria will do that too. Okay, well that's good. So this works like a little battery, doesn't it? Break off a phosphate, use the energy, and now you have to recharge it. The mitochondria can recharge it and put it back together again. So when I say, what are the little batteries in the cell? Guess what some students say? The mitochondria. And I say, no, it's not the mitochondria, it's the ATPs. And you can regenerate, recharge it. All right, is that interesting? See, I think it's interesting. This, and the beautiful pictures help so much, okay? See, they even call them Rome's here. I don't know why people didn't know those were there, but they did. I was surprised. Some words are young, some don't know. Oh, did we do this? We didn't do this. We have to go back and do this. It's not a big deal, but we need to go back. So now I'm back over here. I got caught up with the amino acid stuff here. But if we come up here, that's our friend, isn't it? Most people would say, no, it's not. But this is a steroid, isn't it? Having these rings. Who's made from this? Good old aldosterone. And cortisol. And sex hormones, testosterone, estrogen, progesterone. What is this stuff? When it has these rings like this, it's called a steroid. So this is cholesterol. You have steroid hormones, we were just naming them, that are made from cholesterol. Okay.
Cholesterol is just the yellow portion of that?
No, it's actually the whole thing. Well, yeah, I think the cholesterol is the whole thing. Because they've got this group over here stuck on it. This is typical, but they have groups on it. But this is the real thing, this is the cholesterol.
The entire thing.
I think the whole thing is the cholesterol. Yeah, the whole thing would be a steroid.
So is cholesterol a steroid?
Yes, it is. Well, we did pretty good with that, didn't we? Okay, let's see something else we can do. Something, oh, I don't think I asked you this, I was missing the side of the pages. You got some twigs here in your backyard, or green twigs actually. What do you really have here?
Start.
animal starch called glycogen. And so you tell the liver to break it down. Who tells the liver to break it down? What? Say that again. Hypothalamus? Maybe somewhat. But who's the main message here? Liver, break that down. I wouldn't say that completely. Interesting. What's it? No.
Thyroid.
What's it?
No.
We're running out.
No, I'm gonna give you it finally. Who says break down glycogen? Glucagon.
Oh.
Where's that made? No, don't give me that short answer.
It's in the alpha cells and the
Alpha
islets
cells
of
in the
Langerhans.
Langerhans in the pancreas. And so what do you get? Glycogen will now be changed into glucose. You break it all down. And where do you put them?
In your blood.
In your blood. So anybody wants them, they can use them. Okay. Who makes glycogen? Liver. So who will break it down? Liver. It just have to be told to do that. Okay? So you get a bunch of glucose. So that goes into your blood. So what did it do to your blood sugar level? Raised it. Who lowers blood sugar? Insulin. Where's that made? Beta cells in the islets of Langerhans in the pancreas. What's it do?
It breaks down.
It lowers.
Lowers blood sugar. Yeah. So what happens if somebody who's diabetic takes too much insulin?
Blood sugar crash.
That's right, it crashes. Blood sugar crashes. Is that dangerous? Oh, yes. Okay, have you heard of the young mother who trained the child, if I'm lying on the floor, call 911? Have you heard of that? They saved lives that way. The child did it and saved their mother's life because it was an insulin reaction, too much insulin. If you're taking the insulin, you gotta have the sugars